Good afternoon and welcome to our Thursday afternoon weekly colloquium series. It's my pleasure today to introduce Dr. Hong Fu. Dr. Fu graduated from Sichuan University in China in the physics department in 1982. He then went to Academia Sinica in Beijing for a few years, and from there he went to Stuttgart University to get his Ph.D. in theoretical laser physics with Professor Haken. He graduated in 1989. At that point, my colleague Pierre Meister and I were looking for a postdoc, so we hired Dr. Fu to come and work on an experimental project with us in optical data storage. So he had not done any experiments until that point. He was a theoretical physicist. He went to the lab and he started doing experiments, and within 2 years he was a great experimentalist. The industry couldn't wait to take him out of our department, and in 1994, yes, at the end of 94, he left us. After 4 years in our group, he left to go to Silicon Valley and work for the industry. And he has been there ever since. He has worked for several companies. At one point, he was managing the manufacturing team at JDSU Uniphase. He had something like 500 people working in his group. Remember, he was a theoretical physicist. And that's what we did with him. And then he moved on to other companies for the past 7 years. He tells me as of yesterday, it has been 7 years that he has been working for Johnson & Johnson. And he's going to tell us today about his work at Johnson & Johnson on laser application in vision correction and cataract surgery. Dr. Fu.
Thank you very much for inviting me to be here. So my talk will be maybe 50 minutes around the laser surgeries, everything to do with refractive surgery for cornea and presbyopia and laser cataract surgery. And I want to spend a few minutes talk about how that I feel a student should transfer from a student to a good industrial contributor. So, of course, it's my own opinion, but I worked with a lot of engineers and worked with several industries, so I see a lot of things I want to share with you. And actually, I also want to share with professors, so that when you teach students, what are the things that needs to be to pay attention to. So, next page is the. Let's start with first about the surgery. So the first thing is that I want to introduce the eye. It's strange for an engineer talking about optics in front of optics professors, but I still want to do it. So the eye have 4 key components for vision. Okay, the first component is cornea. It's the most power, refraction power is on cornea. Okay, it's a 42 diopter. What is mean by 1 diopter? If you have a lens focusing a light from infinitely far, and the focus is at 1 meter, that is 1 diopter. Okay, if it is focusing in half meter, that is 2 diopter. If it is 10 diopter, that is focused like 10 centimeter. For example, my eye is 8 diopter. So if I don't wear glasses, I see something here. So that is 12 centimeter, and if you 1 over 12 centimeter is in meters is 8 diopter. So that is my myopic eye. Okay, the second component is the iris. I want to say this because our work is to have something to do with all these components. So that's why I want to explain it. We are going to have a lot of work to do with the cornea, how to change the shape of cornea to improve the vision. And also there is some product that is using a pinhole. It's actually limiting your iris size to get a better depth of focus. And the third component is the lens, crystalline lens. And when we were a child, our lens is so flexible. It can change like 20 diopter. So 1/20 is 5 centimeter. In other words, if we are young, we can see focus here. So in other words, if you have a baby, okay, you can see. You put a finger to his ear, you can see it very clearly. And then gradually you lose it. So that is called accommodation. Okay, so the ability to adjust the lens to see far and near, this ability is called accommodation. So there are certain, like disease, or it's not disease, it's the weaknesses of our eye, like presbyopia. When you become aged, you lost that accommodation. You can only see, for example, if my eye is good, I can see infinite far, then I cannot see close because my eye cannot adjust. So that is one thing associated with the lens. Another thing is when the lens become opaque. So that is a cataract. Then we also treat it. So that's why I want to explain it, this. And of course, the fourth component is the retinal. And that is, I think, at this point, is the only component we cannot treat. Okay, so if people have a retinal problem for vision, there is no known, very repeatable procedure to treat. But there is some like a retinal detachment. Then it is very well known. There is a way to do it using laser, but that is not within this talk. So it's very interesting that our visual acuity limit is it's pretty physical. So there are several limits. Okay, the first limit is that the cone receptor has a natural dimension, correct? That dimension is about 2.5 micron. So what does it mean? It means that if you put a chart, eye chart, slant chart in 6 meter distance, that means that that letter line width have an angular span of about half minute. 1 degree is 60 minutes, so half minute. So in other words, if you look at the slant chart, the lowest one is fundamentally a visual acuity limit limited by the size of the cone. Another limit is actually the diffraction. You know that there is an area disk, correct? If you have a pinhole, you have a plane wave come through the pinhole will cause diffraction, and there is going to be patterns, correct? So the nearest 0 to 0, that is the first, this is the area disk. And you can calculate easily with this formula that if your iris is about 5 millimeters, 4 millimeters, which is typical for our human, that diffraction limit is also about 2 micron. So in other words, 2010, that particular letter line width is basically our limit. And why we want to know that? That is actually for us, our product developer, we want to know, okay, we want to achieve that. Okay, if we achieved that, we know we cannot do better. But if we cannot achieve that, then we know that is the room that we can still do work. So this is a so-called point spread function. What that means, I think this name sometimes sounds very academic, but it's in our engineering term, it's very simple. You put a spot very far, let that spot shiny, and you ask yourself, what is that spot imaging of that spot at your retinal? That's it. Okay, so if the only limit is the diffraction, we should see this. So in other words, when the iris is very small, small pinhole, big diffraction, and then large iris, 7 millimeter, we're going to be very sharp. But what reality shows is different. Every eye have high-order aberrations. So in other words, if you look at your cornea as a, let's say for the simplest case is a spherical surface, if you only look at a very small portion of that spherical surface, then the aberration is very small because aberration, you know that if you are infinitely small, then it's actually a tangential plane on that spherical surface. You are a plane, and then there is no aberration. But if you are bigger, and then any irregular shape will introduce wavefront error relative to the other parts of the eye. So the overall effect is that a point will form a strange imaging in your eye. So I do not know if you ever had the experience of have eye dilated. In other words, if a doctor want to see certain things in your eye, they put a droplet, let your iris open, and many times you will see strange things, and that is due to iris is bigger, all this high order comes in. So I want to show here because this is also our opportunity. So average human eye have a pretty high order aberration. Actually, it's a 0.3 micron RMS wavefront error. You don't need to remember the number, but I think it is actually quite drastic. So if we can address the high order, then we actually can improve even a normal person's vision to be much better than normal people have. For example, not everyone have a 20/10 vision. Okay, if you do 20/10, as I said first, half arc minute, then we cannot do anything. That is a physical limit. But even normal people, usually it's like 20/20. That means you resolve 1 minute of angular distance. So we still have a room from 1 angular arc minute to half. That is a lot of improvement. So that's why this shows us if we can address high order, we can improve the vision.
You said that the cones are 2.3 microns. What is the size of the rod?
I do not know. Yeah. The rod is on the side. The cone is in the covea, in the fovea region. I think it is on same order. I just don't know the exact number. I think in my page 1, I think I had those numbers. Yeah. Another strange thing about the eye, which is also very useful for us in terms of making a product, is the dynamic range of the eye. For example, we want to limit the iris, then we actually also limit the amount of light goes into your eye. Then the question is that if I limit your iris, are you going to feel that it's so dark? So that's why this chart is very useful. It says no. You can cover like an order of 13 orders of magnitude of intensity. And at least 4 or 5 order of magnitude, you have good vision. So let's say if I reduce your iris from 7 millimeter, biggest, okay, no one normally have 7 millimeter, to 1 millimeter. So that is 50 times, okay, 7 times 7 is 49. So it's about 2%. That for this range is nothing. In other words, if I limit your eye from normally, let's say normally we are like 5 millimeter to 1 millimeter, that is 25 times less of 4% of the original. In this chart, it's nothing. You will have good vision. That is actually one of the principles we're using to treat the eye. Just so you know that, that a human can detect like a few photons. Like I think that one of the earliest work done by German scientists in 1940s, they found that the eye can detect 5 to 9 photons. It's just amazing. So that make me doubt about evolution theory, because I think there's never a need for human to detect 5 photons. So that means it's not an evolution need, but it is there. So anyway, interesting. Okay, the other one is that shows that, okay, when the intensity is too strong, it will burn the retinal. So that for industry is very important, because when we design tools, First thing we want to make sure, and no matter what condition, your eye will not be burned by the laser. So we need to know this. Actually, there is a good so-called ANSI standard, and that we can follow. So next time, a few slides talk about measurement of your vision. And of course, we all know, I think probably you all experienced, especially I experienced so many times of this. This is called manifest way of using this phoropter to measure eye. So basically, there is a bunch of lens, a bunch of cylinders, and then the doctor, add 0.25 minus 0.25, then ask you better, worse, better, worse. Eventually, you add all this together, and then your vision is measured. Okay, the good thing of this way is that it goes through your brain. Okay, your vision has something to do with your brain. So the good thing of this method is that you know what you are going to get. For example, the doctor, the optometrist measure your eye, and you said, okay, it's good, good, good. So actually, at the end of the day, after this measurement, you actually know what your future glass will give you, because you were seeing that, you were telling that. So this is a good thing of this method, but it is too coarse, 0.25 diopter, and also it only measures low orders. What does low order mean? Means that if you expand the wavefront into using a complete orthogonal series of functions, like a Zernike polynomial, you have low orders, high orders. Okay, this way only do your low order, second order, because you cannot make high order, because high order is very irregular. It will make this thing like infinitely big, complex. So that is a shortcomings of this method. And there is another way of measuring the eye in a very objective way, is to measure the wavefront aberrations, wavefront distortions of your eye. And I think no one is more qualified than the person in this building talk about this, but I'm still going to talk about it. So this is the Shack-Hartmann sensor principle. I think it is very important to understand this, because if for all this key technology, if you do not have a complete understanding of it, then you will never be able to use it. So therefore, I still put it here so we understand it. So you think about, if your eye is perfect, what it does is that if you're sending a plane wave or a point in the infinitely far, then the light come to your eye and then goes through your eye, focus on the fovea, focus on one point. That means your eye is perfect, correct? You see very far, it come to inside is one point. And the light is reversible. So that is the principle that this device is designed. So it does this. It sends a beam, focus on your cornea. Focus in one spot. You must make sure that. Okay, then the scattered light goes out. So think about the light is reversible, meaning if all your eye optics are right, this point come to here should be a plane wave. A plane wave goes to a lens array, will be focused on an equal distance grid. So when you see equal distance grid, then that means your eye is perfect. You don't need any treatment. If this spot in your detector shows, some distance being different, then that means that wavefront is not perfect plane wave, and that you can reconstruct. Okay, by this tilt, by this focal length, you can actually reconstruct the surface, and then you can tell, okay, what is the wavefront distortion. Then you expand. That is how this tool works. Okay, expand this distortion into a bunch of Zernike polynomial orders. And usually when we treat, for example, normally our eye treatment is treating these three terms. So basically this is myopia, And this is so-called astigmatism, or some people call it cylinder. So that is actually a cylindrical surface. We produce a cylinder. So this is actually a normal glass contact lens, all treated this. But with wavefront aberrometer, we actually can treat. I mean, we at least can test, okay, can measure higher order terms. And as I said before, higher order terms have an effect. Okay, it changes the point spread function into a very irregular, unpredictable shape for different people. Okay, for same person, same higher order distortion in the cornea or in the eye, that pattern is fixed. But for different people, it's all different. So I think that what I want to mention here is that we know our opportunity here is that the higher order terms can be measured and they should be treated. But today, actually, this is not done very successful. I mean, there is a lot of effort, a lot of system claims that correct high order, but due to a number of reasons, not only due to the machine precision, which is also part of a good reason, and also due to the tissue post-response. Let's say after surgery, the tissue does not always acting as we ask it to act. So those tissue responses are different. That can also cause that this term is not treated as planned. Yes, yes. It's, we actually do not dilate. What we do is that we cause the illumination condition to be very weak light, called mesopic light. So during that, just like put you in a dark room, then your pupil automatically become bigger. And then it is measured.
Do you use different colors to measure the chromatic aberration as well?
No, this is not. This is all 870 nanometer light. So that we have not come to that point yet. Yeah. No. Today's measurement is only single wavelengths. Yeah. So once we measured the wavefront error, and now we ask ourselves, okay, how do we correct? So it's very simple, correct? So let's say, you think about this also with single point light in your retinal and now it's emitting light coming out. So if the eye is perfect, it come to a plane wave, but if the wavefront come out is like this, then actually what the treatment will be a kind of inverse the shape of this because, for example, let's look at one. Let's say, look at this point. The wavefront is delayed, correct, relative to this one. That means what? That means the tissue is too thick because tissue have a higher index. So the light goes through more tissue. The speed of light is c divided by the numerical, by the refractive index. So the light is slower. So that there is a phase delay. So what we do is that we're going to cut or remove this amount of light. So then when we remove all this, reverse to this, actually the relations by this formula, then we can correct low order and high order. So this is a chart that shows what average person, let's say average person have a perfect low order. In other words, you remove your glasses, you can see perfect, but you still have high order. So this means that if average persons have no problem at all, just have low order being completely corrected, and then his contrast sensitivity or the modulation transfer function will like this. What is meant by modulation transfer function? Fundamentally, it means that how this peak, this valley peak difference to show how contrast is. So if we can treat high order, we're going to get this. In other words, our modulation transfer function will be higher. In other words, the contrast that we see will be higher. So this is the opportunity for our treatment. Say, yeah, if we can treat high order, then everyone's vision will be improved. And the industry usually use this kind of name called supervision, but that means this. Yeah. So Next one is going to talk about femtosecond laser. So femtosecond laser, you know femtosecond, okay, it's like 10 to minus 15, but again, it's industry. And we actually is, for example, 800 femtosecond laser. We should call it a near pico, but industry always use femtosecond laser, never being 1 femtosecond. So now the shortest femtosecond laser on the market is about 250 femtosecond. And when this product comes to the market, it's about 600 to 800 femtosecond. So just to give you a sense, the light in this pulse width propagates like 100 micron-ish. So like if we use 150 femtoseconds, the light propagates 45 microns. So in other words, a femtosecond laser generates pulses. If you can color the pulse, what you saw is a disk. Okay, everyone, it's a very thin disk. This disk is only 40 micron, 100 micron, 200 micron. Like this one is 180 micron, very thick disk at one disk. So in other words, the laser produces one disk after the other in a high frequency. So that is a femtosecond laser. How it generates is this. It's first have an oscillator generate a very short pulse, and using a so-called mode locking method. If you know Fourier transform, okay, any sharp function when you transfer into Fourier series, you have a lot of terms, correct? If you have only sinusoidal, then you transfer, it is only one term. Okay, if you have a very sharp, kind of discontinuous peak there, if you want to transfer, that is many, many terms. If you transfer delta function, you have infinite many of terms, and every term is a constant. So this so-called mode locking, for this particular laser, is we actually have 11,000 longitudinal cavity modes. And we want all these cavity modes oscillate in phase. In other words, they achieve maximum at the same time. When they add together, we got this very short pulse width. And then the light is the pulse energy is too weak, it cannot do anything. And we need to amplify it. But we cannot amplify the original pulse because this peak energy is so high it will destroy optics. So the way to do it is that to stretch it, but keep the phase relation. So in other words, this stretch can be reversed. Make it very shallow, very low, so the peak energy is very small. And then we send it go to amplifier, so that the energy is very high. And then remember, all these Fourier terms are still keep the phase relation. So we use a compressor. It's a grating, okay. Let the pulse go. Originally goes the first, delay it a little bit. The pulse goes very slow, accelerated, so that all these pulse coming together in time-wise. So they add together, you get a pulse. And this pulse now is sufficient to generate a tissue effect, laser tissue effect. You know that your cornea is transparent. So if you send a transparent thing to the cornea, it just goes through without any effect. So therefore, we need this very high peak power to generate the effect. This is called, to generate a plasma effect. So the femtosecond laser is working is like a thunderstorm, okay, the lightning. So basically, we focus that short pulse spatially also into a tiny spot. So now the energy density is extremely high. And then it ionizes the electrons. And that ionization itself generates absorption because you have more electrons, and then it absorbs the next light coming. So even in a transparent medium, it generates effect. It generates a self-absorbing impact in a very short time range. There is no heat. That is actually key also. We cannot process your cornea with like heating it, and then your cornea will become opaque. That is no good. So One femtosecond is timely, it's very short, spatially it's very tiny, and it generates the effect, and then it generates the plasma will convert into a cavitation bubble, and that small bubble is micron level size. It will separate the corneal tissue. And when all small separations are connecting together, that forms a surface dissection. So two-dimensional separation. That is how it works. So this is one of the work done by University of Lübeck. And what they shown is that how big is the cavitation bubble as a function of wavelength, as a function of energy. And it is very surprising. What is surprising is actually is also very obvious now, but it's very surprising is that there's no relation. It's actually if it is only at the threshold level, how do you introduce that plasma? That have a lot of relation to do with wavelengths, pulse width, and so forth. But once you are sufficient above the threshold, they form a very well-defined asymptotic relation. So I think for the university application, let's say if you study application fundamental rules, this is the rules that are very useful for industry. So when we see this, we know immediately, okay, whichever wavelength is fine. Okay, of course there's other impact. For example, one time I found a laser who can operating at 512, a green laser. It's cheap, low cost, meet all this condition. But then I talked to our laser safety guy. He said, 512 is like our eye is most sensitive. During the treatment, and the patient will directly see the sun because it is so the response, the retinal response is the strongest. So it's not possible. But I think in terms of bubble cavitation, tissue separation effect, there is a generic rules on it. So to do eye treatment, there is another type of laser called Excimer laser that is used to remove the tissue, to reshape your cornea. And this laser actually generates a pulse of a few nanoseconds. It's a UV laser, at a 193 nanometer. And its mechanism is different from the femtosecond laser. Its mechanism is just the photon have a high energy, 6.4 eV energy, which is higher than most of the bonds, like CH bonds and so forth. So when shining this laser to the eye tissue, it just directly breaks the bonds without generating any heat and create a very smooth tissue surface. So that is exactly what is needed. So when we have these two lasers, femtosecond laser, which can produce an incision, and we have this Excimer laser, which can remove tissue in a very precise manner, the industry is formed to do surgery. So there's quite several companies produce the system. So have the femtosecond laser to do incision and have the Excimer laser to do tissue removal. Together, they can correct the shape by design for the purpose of the treatment. I put it here. I also have a purpose for the students. I think that when you go to industry, your company is always competing with some other company. Therefore, you have to have the view of the world. Otherwise, you think the best idea will not, most of the time, will not be viable because you really need to know the worldwide thing. And actually, no company will release any more information. They have some. So actually, we need to study paper, follow conference, put all these anecdotal things together. And I mean, physics is the same, correct? So then you actually can kind of tell how each company is doing and why they do that, and then come to a better design. And that is, I think, is very important because the product has never been, I think, especially personally, I have never been found. I have a very original idea of a product that no one had any predecessor. There's always something similar. It's just like a patent, just like a Nobel Prize. Okay, any work, Einstein's work, whoever's work, there's something before. So you need to see all of this and come to a better idea.
First thing that each system has 2 lasers, one femtosecond.
Correct.
One Excimer.
Correct.
We need both of them.
We need both of them to do, yeah. Before, actually people use so-called a microkeratome, which is a mechanical cutter to do the cutting work. But actually just a few weeks ago, 3 weeks ago, there is a doctor visiting me. He said, I appreciate your work. And he said, before I use microkeratome, a few hundred patients, very small, correct? It's less than 1%. I had a problem, I completely moved their cornea without control because mechanics think about you have blades, okay, very sharp, cutting your cornea top surface. You want to cut it in a very controlled manner, day in and day out. It's very difficult. So the doctor says, I'm nervous, even though I have, he said, it's every 300 patients he has one. But once that happens, what do you do? How do you tell this patient? I said, hey, sorry, today my tool doesn't work well. I removed your cornea. So it's very difficult. So therefore, that tool is very cheap. And this femtosecond laser is like a $250,000 tool. But doctor appreciated it because we removed their stress so that they can cut reliably. They can control the shape to the microns. So that is technology, correct? You make something analog to digital, become controlled, become independent of hand skills. So on this tool, there is one part is very important. Is when we cut your eye, the eye needs to be fixed, correct? If let's say I put a femtosecond laser catching eye, and your eye is moving, so that will not go. So the device that grab your eye is so-called a patient interface. What it does is that it has one portion. By the way, this two-piece is all separate. Okay, we sell a small box to doctor, and actually that's how the company make money. So-called disposables. You must create good reason to say this thing must be disposed every time. You cannot use it twice. You must make that. By the way, all the company making that. And you must create a reason for safety. You say, okay, if you don't do this, it's not safe, not good for patient. Anyway, do it. Do it. 2 parts. One part, you fix it. When you have this part, you fix into the system tightly. The other part is a suction ring. It put on your eyes, suction your eye so that your eye is fixed. Then you put these 2 pieces together, clip it. So now your eye cornea is tightly fixed by the vacuum and then by the mechanical mechanism with the machine. So now your cornea and the machine forms a fixed geometrical relation. Now you can cut whatever machine is programmed to do. Okay, next I want to introduce typical low-order types of refractive error. So for example, people say you are myopia, meaning that you are nearsighted, or hyperopia, you are farsighted, and astigmatism. So there's a total 5 types. Okay, if you let's say look at let's say if light come to you as a beam, okay, this beam, and if you separate the light, say I look at the different sections, so we call it a meridian. Okay, let's say you look at one meridian, like light coming from here like this, and the light come from here, and if these 2 beams focus at the same point, then but both of the points is in front of the retinal, then this is called a pure myopia. Okay, in other words, your corneal surface is still spherical, but just the curvature, the radius of curvature is too small. The focusing power is too strong. So the light is focused too much. And so this creates the myopia. And if these two meridian of light coming focus on different location, astigmatism, or we call it cylinder. And then hyperopia with astigmatism. And there is another one is called mixed astigmatism. Is that it's one meridian of light focused in front of the cornea, and the other focused on behind the cornea. So anyway, this is the names because the treatment for this are different. The physics of treatment is actually very simple. So as I said, myopia means that your eye is focusing power is too strong. So if you think your eye is just a glass lens, then that means this lens is too thick. Then you need to remove some material. And that's exactly what we do. And that how much you remove is very easy to calculate as long as you know the index of cornea. So basically, is follow a very simple relation. By the way, this relation actually was done first by an engineer graduated from University of Rochester. So it's not from here. But yeah, it's actually, so the message I want to deliver is that if you look at a great invention, the formula is very simple. This is high school optics. Correct? High school teach you, you have spherical surface, where is the surface? Where is the focus, correct? Let's say if you have a spherical surface, the radius is what? It's like r divided by n minus 1 kind of thing. So he's thinking, okay, if you are too high, and how do I reduce it? And then he make this. This is really easier high school physics or first year university. And he actually opened the entire field. This is actually the first treatment of the eye with a numerical instruction to the system. And then even today, this is the fundamental. Okay, we can do high order, but as I said, high order has still something you guys need to fix in the future. And this is still the way that we are doing. So if you want to remove one diopter, it's about 13 micron of tissue to be removed. And your cornea is about, what, 550 micron? So usually we say the cornea needs to be 300 micron or above. So that means you have no more than 200 some micron to be removed. And of course, if you are 10 diopter, you remove about 130 microns, still about a quarter of your cornea. So if it is a myopia, you remove it such that this is before remove the curvature, and after remove it's become more flattened. And for hyperopia, just opposite. You remove the side so that the curvature here is increased. A very simple principle. Yeah, that is the key. That is the key. That is what I'm going to talk now. That is why we only treat the central layer called the stroma. The stroma is this is a cornea. Okay, the human cornea have 5 layers. 5 layers. The top layer is called epithelium, 50 micron-ish. It grows within 24 hours. So that is, I think, the creator or the God designed the human so that if you are, like injured, it will grow back. But on the other side, your eye needs stability, correct? If every tissue in the eye can be grown, then you will never have a stable vision. Think about it, because eye is a very precise optical system. It needs to be stable. So God designed this layer, 500 micron, to be no grow. That create the opportunity for us to do treatment. It's actually amazing. I think this is really amazing. So, but to treat this layer, we have to open the top. That's why we need a femtosecond laser to create an incision. We call it a flap. It's basically it's not a complete circle, but it's more than half a circle, and then you open it. Then the tissue is exposed. Then we use excimer laser to remove certain tissue, to the shape we want. And then we put it's called flap back. I will explain a little bit more here. So basically, this is step one. This is called the LASIK procedure. So far, I think it's about 40 or 30-some million eyes being treated with this technology. So the first step is that we use femtosecond laser to create a flap and open it. So now the stroma material is exposed. And this material does not grow. If you remove it, it will never regrow back.
But how does it heal if it doesn't grow?
It does not heal. The only thing heal, it is the top layer. So in other words, that layer is always there. But it has a very natural, good adhesion, but it's never been so strong as the original. But on the other side, you think that the corneal structure is a laminar structure. So in this direction, it's never been strong. Because it cannot be strong because you need your eye pressure to push the eyeball so that it is good spherical surface. So it needs to be kind of soft. All this is like very precisely designed by someone. Okay, the next step is using Excimer laser to remove the shape that by design. So in other words, there is an algorithm. Say, okay, you want to remove this shape. I will instruct the machine to do how many pulses here and there in a controlled manner. And so that the shape is created per the design. And then the third step is to put the flap back. When the flap putting back, the original cornea, let's say original is like this shape, now become this, so it become more flattened. Then the light will be focused to the retinal. So this is the LASIK procedure. This is the patient interface to suction. And now it's cutting the flap, the femtosecond laser. This is a cavitation bubble, separate tissue at about 100 micron deep. Okay, now the doctor using the tweezer to open the flap. Now the stroma is exposed. Now Excimer laser is remove the shape that you want to remove. Now the doctor remove the debris. Put the flap back, and the edge of the flap, as I said, because it is epithelium, will grow within 24 hours.
How did you figure out how to use optical tweezers to
You need to be back removed.
No, you can do optical tweezers. As long as you have wavelengths that can transfer momentum to the flap, you can do it without mechanical motion.
Wow. That will be transforming. Yeah. So this is a follow-up. One patient finished that procedure. This is one of the clinical study. For all the equipment company like us, this is one of the most difficult step because it takes like usually 1 year. So you need to recruit patients, do the work, compare the results. So what it shows here is that, like 20/20 is the standard. So 94% of people get 20/20, eye being treated well. And lately, there's a new technology because the femtosecond laser technology is improved. And we ask ourselves, why do we even need the Excimer laser to remove the tissue? We just cut the shape we want to cut, and then remove the whole piece. So this is not Still not yet optical tweezer, just a tweezer to get that out. So this is the way that lately Zeiss is doing. So I think the advantage of this method is that the opening can be very small. You don't need to move like a big piece, open it. That process is gone. You cut, and then you have a small opening, you get that piece out. So it's much less invasive. I have a video here. I do not want to show it too long. This is cutting that so-called smile, what I just showed, but you can imagine it. Okay, so it's cut this surface, that surface, get it out. But the process to remove that tissue is intimidating. So I don't want to show you, because I saw you guys already feel the last one is aggressive. This one is like, move your eyes back and forth, get things out. That provides an opportunity for all of us, for me, for you guys, to improve the procedure. So this is the result of that so-called smile procedure, cutting, using all femto laser, cutting a lenticule and extract out. It's pretty good. So fundamentally is this. We look at 2020 percentage. So first week is low, and then it's gradually to be high. And this is not like LASIK. LASIK, first week is already high. It's like 90%. So people have done some study to show what's happening. What they found is that the femtosecond laser actually affected the roughness, light scattering of the cutting interface. So therefore, now people want to study how can I minimize that light scattering. And for that reason, actually, I talked to DK today, and I found he have a tool. It seems to me is immediately applicable for us to do this study. So we want to follow up with that.
Wait a second. So 88% get 20/20 or better. But another important statistic is, are the other 12% blind after this?
Oh, no.
So what percentage?
Yeah.
What percentage is really a disaster?
Yeah. To answer your question is that no. So for example, 2040 is 100%. So 2020, say 88%. If you open that, say 2040, I also count as successful, then it is 100%. And actually, you can also see here. Here it shows this. After treatment, I still put a lens here. Say, hey, look at here, which is better. And then we use a 0.5 diopter lens. Okay, negative, positive. So if I put positive, negative, you both say, no, this is worse. Then I don't have any. That means you are within plus minus 0.5, and that is 93% is very stable. Yeah. So to answer your question, those never occur. So I think the worst case is that there might be a short time glare, halo, and that is a side effect of this treatment. It will, I have not seen like people, blind definitely will not, because this treatment itself is move a very thin layer of your cornea. There's nothing really drastic to, for example, block the light. Okay, next one is talking about presbyopia. So-called presbyopia is that, as I said in the beginning, the crystalline lens become hardened, so you lost of accommodation. So when you are young, your crystalline lens can change, adjust, so that you can see far and near. And actually, this has been the people who realized this actually got a Nobel Prize. And I checked for all the Nobel Prize. There is only one Nobel Prize for the eye. That is this person who understands how humans see far and near. And although, even in Kepler's time, 500 years ago, he did all this anatomy of the human eye, and he already knows the lens is changing for human to see far and near. But he understands is that, you know, that it's not just you change far and near. Every step you need to form a good imaging. You think about it. It's not easy, okay? Your lens have like, we don't control the shape, at least we do not intentionally control the shape of the lens, correct? You just see far and near, and you find that your lens actually is moved in such a way that in every step, high order, low order, everything is like perfect, or almost perfect. That is the key. So he's the person who realized this. Today, there's a company like developing products that say, hey, if you're old and you lost this so-called accommodation, you can only see far, or you can only see a given distance, no adjustments, and their company developed different products. But none of the product is like a original human to adjust the shape so that it completely recover as you were a child. So I think, it's not I think, everyone think, this should be a Nobel Prize if any of you can develop a deformable mirror in a soft way controlled by your muscle or in a natural way that it can reproduce human original lens. I think it's a Nobel Prize because you will improve the quality of life of 100% of human and who are above 40, 50 years old. Everyone. No exception.
It's a problem of old age that the muscles have lost their ability to adjust, or the lens has lost its ability.
This is a good question, but I think the consensus is the lens become hardened. It's not the muscle. So therefore, actually, there is a new product designed. They remove the lens. They put another mechanical lens in it and still use the human ciliary muscle to adjust it. But none of them being successful. Yeah. So this curve shows, how many people, percentage of people lost how much accommodation versus age. So basically, let's see this. So when you are very young, you can adjust 20 diopter. In other words, you can see 5 centimeter here. Okay, when you are 60 years old, you can see here, and then you cannot see near because your lens is hardened. You cannot adjust. So the way to treat it now, today, is actually very, very primitive. Okay, so let's first explain it. So let's say this is the lens. Now it's hardened, so it's fixed just like a glass optics. Infinite light, focus on retinal, perfect. For the same lens, of course, by lens formula, you know that if you move that object to near, then this imaging will be far. Okay, then at the retinal, the spot will be big. That means the so-called point spread function become big. That causes the vagueness. Okay, you will not see things clearly. So how we treat this today is very crude, but this process is this procedure is like $8,000 per procedure. What do we do is this: you cut the cornea, make a pocket, make a bag, and put a small lens into it. So this lens focus center beam into the retinal. That is one way to do it. Another way to do it is to make a pinhole. So you put a pinhole here, limit the peripheral light so that those light can pass the pinhole, still focus here, but at the retinal, the size is also small. So this can improve your accommodation a little bit by 2 diopter. This actually is a product. And the procedure for this one, put a piece of pinhole in your eye, cost $8,000. So in this regard, what Femtosecond to do is very simple. Femtosecond just create a pocket. So we cut a pocket in your cornea, and then doctor will get from another company, get either the micro lens or the pinhole insert into it. But of course, by the way, all this pinhole is not that simple. Okay? It has to be biocompatible and has to have to be allow the nutrition flow, a lot of science into it. And a company just do that is many years, a lot of people's effort. So just some credit for the industry. The next one is cataract. Cataract is also about the crystalline lens, but it is about the lens become opaque. Okay, there is many mechanisms so that the lens is opaque, and one of the known mechanism is the UV light of the sun. So, for example, for people live in like a beach, close to beach, and there is a statistics shows that there is more chance because the light reflects from the sand is actually very strong. So if you're a long time exposed to those light, you will have a higher chance to develop cataract. Then your eye become opaque. Actually, this was the #1 reason for blindness before. I think it's no longer because there's a good treatment of this. So look at here is the chance of ages and how much percentage of the people have the cataract. So when you have cataract, then you cannot read very well. And like when I do the, my eye doctor check me, and he put all this lens, say, hey, better, good, better, worse. He found actually there's no lens can make me feel better. Then he said, maybe you have cataract. So then he put a newspaper with very tiny letters. Okay, he said, you look at the newspaper, do you see everything? Oh, I found that at one location the newspaper is white. He said, no, this newspaper have words everywhere. Then he said, okay, you actually have a light degree of cataract. So the treatment of cataract has been very mature. So there is like every year there's approximately 20 million eyes being treated. So you think about this, it's actually for industry, this is a big business opportunity. Okay, so how do we make the machine to do the cataract surgery, and how do we make the artificial lens, we call it intraocular lens, IOL. How do we make the lens to replace the human crystalline lens? That becomes huge business, and that is actually, by the way, is very beneficial to humankind. So that actually this being considered to be the best, the quality of life improvement procedure. So what it does is original way is using ultrasonics. So what it does is that using a blade cutting your cornea, making a 3 millimeter puncture, a 3 millimeter hole, and then they put tools, put the ultrasonic tube, probe to break the lens inside, and then they suck the broken pieces out. So then your eye, that lens is in an empty bag. Okay, that is called capsule. And then they insert a lens into that capsule. So then your eye is being treated. That cataract is being treated. So lately, try to reduce the amount of work done by the ultrasound system, and also try to avoid knife cutting. So there is a system, laser system is developed for that purpose. So what the laser doing is this. Okay, so first, let's say it cut an opening 3 millimeter hole so that your tool can go into it. And also, the laser can cut the capsule. You need to cut the capsule open so that you can break the lens, the opaque lens. And also there is one laser step is to break the cutting. It's cutting the opaque crystalline lens. It's called lens fragmentation. So this shows that, so this is called capsulotomy. So laser cutting a very circular hole in your capsule, in which the lens material is in. Okay, so lens is in a capsule. This capsule is very thin. It's about 20 microns thick. So this is a laser cutting a circular capsule, and then this top part is removed. It's open. And this is a human. So right now it's like 80% of the procedure is done by manual. So doctor basically put a tweezer into your eye, grab one piece of your capsule, and then doctor just do it. And doctor actually very proud that they can do it circularly. But no comparison with laser. But by the way, there is no disadvantage also. This actually is a very well received procedure, very effective, but it's manually dependent. So like if you are new from medical school, probably patient don't want you to do it. So if you're using a laser system, then you don't have that problem. You can do as good as anyone. So yeah, I take a few more minutes, but I think let's do it. Still do it. Still 10 minutes, but I think it's sufficient to show this. I'm almost done. So this is a laser cataract surgery. The first is the doctor so-called planning. So they put, okay, what I want to cut, how deep, how long time, what is the size of capsulotomy. And this is a patient interface to fix your eye, put some water so that the light can pass. And then doctor measures, this is OCT imaging, to measure where is your lens so that he can deliver the laser to that particular location. So now it shows how they are going to do so-called lens fragmentation. Basically, laser going to cut. And this red area is a safety zone. So they say, okay, I measured, then these are the boundaries I don't want to cut. So you cut within this boundary. And then they cut. Entire process is approximately 2 minutes, maybe. Laser on time maybe is 1 minute, 30 seconds. So now laser procedure is done. And then they still need some ultrasonic to break what is already cut by the laser. And then this ultrasonic tubing, probing, have an inner hole. Oh, that is tweezer. Yeah, this one. So have an inner hole. It actually sucks the material, called aspiration. Don't worry. One day you will be. you will be here.
This is outlawed by the Geneva Convention. It's like torture.
You say it is a torture. Almost all the patients, when get this done, they said, oh, why don't I do it earlier? I know one of my friends, immediately after this is removed, she said, I never seen the world is so beautiful. So it is like, yeah. So anyway, give you a sense. So after that, another tubing, they have the so-called IOL, intraocular lens, in it, warped, to be inserted to the empty capsule, and then it will flatten by itself because of material design. And this one have the right focusing power, which is determined by the pre-operation measurement. There's different type of lens. So there is a lens called a monofocal. It is just have one focus. Okay, that is the most reliable, most popular. And there is also so-called a multifocal. They basically have designed different zones to focus different parts into different distance. Then it's up to your brain to choose. Say, for example, it basically have 3 imagings in your retinal at one time. And your brain pick up the one. So some people have no problem, some people forever cannot adapt. So that's why I would say, if one of you can develop this human, this quasi soft accommodative lens, that would be really, really good. So after the surgery, there is one complication which happens also with high percentage of patients, is that in the back of the capsule it will grow a material which seems to be opaque, and this is called posterior capsule opacification. And then there's another laser procedure to basically cut that area. Sorry, this is a poor, the cut better, okay, cut circular, so that that material is gone. That is actually practiced very successfully. I mean, it looks like crude, correct? But it's very smooth. And if some of your parents, have this, just go to doctor, very short procedure, very safe, they come back very satisfied. But, like anything, the more you know, the more you're concerned. Okay, summary. Pretty much on time. So summary is that, to treating myopia, hyperopia, you just remove material. To treating presbyopia, because the lens is hardened, we either put a micro lens or put a pinhole. And to treat cataract, break the lens, put an artificial lens. That's end of my story. I want to spend a few minutes talk to the students because I've gone this process, so I just want to have a little bit of sense, no more than 5 minutes, about the industry. So the product that I explained, usually the development time is about 5 to 10 years. It's a very long time, starting from maybe 1 or 2 people have a great idea, become 10 people, 20, 50, 100, 250, and then become a product. Usually that is the process, so in that many years. And there's a lot of collaboration between, first, of course, is original idea. That person needs to have a good experience, good understanding of science, technology, good understanding of what doctor needs, good understanding of what other company doing. So then become a collaboration project. So many teams, quality, manufacturing, regulatory, engineering, all these teams needs to be collaborating. So FDA have a design control process, and that for any medical equipment, the development is tracked. So in other words, for example, if you one day say, hey, I look at something, I feel it is dangerous, you put on your notebook. All this is very important. You must have somewhere to show this risk being addressed. Okay, otherwise, this is like, you already see something dangerous, your company didn't take any action. So those are the FDA want to manage. This is called a design control process. It's also very lengthy process. Usually when we develop a system, it's like making maybe 4 generations just within development. First make a prototype, prove, then make another system, find some problem, another one. So it's like 4 times. Each time is about 1 year. Because it's very complex to make things work. And then you need to do human clinical trial, which typically 2 years. You need 1 year data, but 1 year you need to recruit patient and then do the work. And also, none of the steps is problem-free. It's always problem, all kinds of. So we need to address the problem. So that's why I came to this. Is for student, let's say you, in 1 or 2 years you are going to go to industry. What do you think? And what do you want to do? So I would say, first the industry have its own culture. And Silicon Valley is not anything special. It's just like any industry, any company. The only thing a little bit special with Silicon Valley is that it's more drastic. So like myself, Masood explained that I joined several companies. I joined 4 different industries. It's not up to me. Okay, the industry just die by itself in a so quick way that I joined 4 industries, 2 of them does not exist. I joined 8 companies, 6 of them does not exist. You just have to keep up. So I think one thing that is always under your control is that problem solving. And this is your value. This is our value. So if you cannot solve problem, you don't have value. You have to solve problem. And of course, in industry, there's all different kinds of problems. In manufacturing, the problem needs to be resolved within hours. Okay, otherwise they're waiting. Okay, in R&D, the problem needs to be resolved within 1 to 2 months. Otherwise, the project will not move forward. Sometimes you go to companies, the company have a known existing bottleneck problem. Those problems usually allows you like half year to resolve. If you resolve that, you make the company progress. Leadership, I would say, let's make it simple. Don't make it like you're managing or whatever it is. I think leadership is just you never wait. You don't find any reason to wait. You don't say, hey, my boss is not here so that I'm waiting for him to prove this. Never. You never wait and never come to your mindset. You always push things forward. Okay, you say, hey, I'm waiting for purchasing material. I'm waiting for receive things. Those are all bad excuses. You can only always find a reason to move yourselves, push things forward. Study the work. I think that being a student, you never changes your study. You study lifetime. The only thing is that you study different things. Okay, now there's no exams for you, but every day is exam, correct? You go to company, a company sees your value, so you must study your work. Anything, don't limit yourself for what you have done with Ph.D. or master. You do whatever that blocks you. You learn that. At the beginning, it's very difficult, correct? You say, hey, I never studied mechanics. I never studied this and that. But once you have a habit of just study a little bit, talk to the expert in the company, you learn a little bit, and it's tremendous. And eventually, it's like an interest that you save your money in the bank. Okay, 2%, 3% is nothing. But after years, the difference is humongous. So I want to take this opportunity to thank you, especially Masoud, who introduced me to, recommended me and educated me to become a useful hands-on person. Actually, I'm not that hands-on, but at least to a certain degree, to be useful for industry so that I found my first job. He actually recommended to me my first job that become my industry work until now. Thank you very much. Yeah.